Good morning and welcome to the FAÇADE webinar series episode 5. My name is Laetitia Marot. I am a Marie Skłodowska-Curie Fellow at the InnoRenew Centre of Excellence. And today we will talk about the potential of carbonized biomass for advanced material applications. Our speaker will be Dr. David DeVallance, who is also my group leader in the Renewable and Composites groups at the InnoRenew Centre of Excellence. Dr. DeVallance has a PhD and a master's degree in wood science. He is expert in the development of bio-based composite materials and carbonization of biomass for making advanced composites. He was an associate professor in the USA, and now he's also the Vice Rector for Internationalization at the University of Primorska in Koper here in Slovenia. The presentation is recorded today. And as usual, you can send your questions in the chat and I will read them to Dr. DeVallance at the end of his presentation. So now let's talk about biocarbon. Dr. DeVallance, you can start.
Okay, thank you, Laetitia. It's a pleasure to be here today to just share some research that has been ongoing and using carbonized biomass and transforming that into other purposes than traditional purposes. In our case, we're looking at these advanced material applications. And so I'll go through some examples today and show you some challenges that go along with doing this kind of work. Once I get it to move here. So first, I thought I'd just, for those that don't know all that much about biocarbon or biochar, just go through a little bit of kind of the historical use of this material in producing things for different materials. In general, the use of biochar started out as being something that is used for soil amendments, but really typically for heating. Initially, this was material that was used for melting silver, used for heating, cooking food over. So there's really a bunch of different ways to manufacture this, and you get different properties depending on which way you do it. But in general, what you're doing is you're doing a thermal decomposition of some kind of biomass in an atmosphere that is free of oxygen. And you can get this oxygen-free atmosphere in a few different ways. You can also do this using a fast pyrolysis method, which is shown in this image on the right, showing this tube type furnace, or you can do it traditionally how it was done in this slow method, where you put a bunch of biomass in some kind of kiln. In this case, it was an earth type kiln, and you light a fire in there, and once that fire gets going, you shut off the exit and you really keep any oxygen from entering. So that would have been the traditional way that this was made for centuries, and then used for producing things for heating mainly. So the main applications are these combustion type properties, absorbent soil amendments for catalysts, and what we're looking at is developing these into materials for more composite related applications. So I've just put together kind of some potential end uses that we think there are some opportunities for using this biochar material. And we start over here on the left looking at biomass from different types of sources. Typically we're focused originally on wood, but we're starting to move research into carbonizing other materials. In this case, hemp, lignin, and olive stones. So you take this material and you can put it through a pre-processing step, and then you go through a pyrolysis step. And then with that step, you can change different things in terms of temperatures, steps, how many steps you actually do, how fast you're going to do it, the environment which you're in. So you can carbonize in a nitrogen environment or an argon environment. We've actually done carbonization under an oxygen environment. Remember before I said you want to do this typically in an oxygen-free atmosphere, but we've actually done it in an oxygen atmosphere up to a certain point. So you can modify these things. The main thing is when you're carbonizing it, you don't want it to catch on fire. That would be the worst end case for making this carbon. And then at the end, you can do things to upgrade it. So we'll look at a few things where you do activation to improve its properties and what that actually does. So here through this, going through this graph, once you modify these materials and you start looking at some kind of carbon raw material that can go into these different applications. So what I have highlighted in blue are things that we currently have had some work in. So I'll go through a couple examples of these materials through the presentation, mainly looking at the looking at the supercapacitors, looking at using this bio-based carbon for composite filler materials, and then looking at it for conductive materials and sensors. And then I'll introduce what this project, this facade project, is actually about, using it in coatings. And we've recently been looking more into, and I have at least one photo of where I was looking before using this in acoustic panels and actually insulating panels. Traditionally, though, you will see this hardwood lump charcoal. In this case, this is Cowboy brand charcoal. And this is really what people would typically use this for. You would go to the store, you would buy one bag of this material, and you would take it home and you would make a barbecue. So a very low value kind of application in this instance. A very nice application, but not very high value, at least. So why are we looking at bio-based carbon? Really what we're trying to do through this research is reduce our dependence on these traditional type carbon materials. So here's an example of going from this renewably sourced material and then making the carbon, like I mentioned in the previous ones. And then here are the current applications where carbon black made from petrochemical oil, coal tar oil, and natural gas are used. So there's a lot of instances where these non-renewable carbon black material are used for making products. So our goal is to try to use these renewable sources and get them to displace some of these other materials to reduce their carbon footprint. So along with this, I mentioned there are some challenges. So a while back, we went through and did kind of a SWOT analysis, and I won't go through all this. You can come back later if you're really interested and read this. But one of the strengths, maybe the biggest strength for using these bio-based carbons is you can, if you develop them right and carbonize correctly, you can get a highly developed porous structure. And that porous structure will help you do a lot of different things. If you're looking to just make charcoal to burn, that porous structure doesn't really matter as much. If you're looking for this bio-based carbon for supercapacitors, then this porous structure becomes very important. So there are opportunities to do different types of processing to get different end products. So along with the strengths, there's some opportunities. Obviously, if we can start replacing these fossil-based carbon materials, that's a benefit to the environment. There's a lot of work just in general in carbonizing, say, plastics or carbonizing textile waste and landfilling that instead of having, and holding that carbon for a long time in a landfill instead of just throwing it away or recycling it. So there are opportunities in using this bio-based carbon. Some weaknesses are the technology, a little bit around cost, but I was on a call the other day where we went through some economics on looking at producing biochar, and it was actually very economical, especially when you get up to 20,000 or 30,000 metric tons per year. It becomes very economical. Probably the biggest issue is what I have listed here, this lack of large individual end users. So there's a lack of bulk sales for this. So as I mentioned, most people or most markets now are set up for people buying these bags of this material. So there are a lot of weaknesses related to the current market conditions. So the first advanced materials I'm going to go through are using this carbonized biomass for electrical properties. And I'll go through some of these fairly quick, and then we can come back to questions at the end if you have some questions. But here's the first kind of real big study that I was involved with that was looking at carbonizing Appalachian hardwoods or low value hardwoods, and also short rotation woody crops. We were taking red oak, yellow poplar, and shrub willow. The shrub willow was grown on marginal farmland and reclaimed mine land, and carbonizing at these different temperatures. And we were doing that for multiple applications, which I'll show in the next slides. In this particular research, we were doing this in a tube furnace at a rate of 50 degrees Celsius per minute, and then holding all the results I will show you, are holding this material in there for 30 minutes of duration. So the first thing, once you start carbonizing these materials, you want to look at are, how much fixed carbon's in there, how much ash do you produce, and then later on when we start talking about some of these properties, the oxygen content and nitrogen content actually become fairly important, and how well they perform in their intended applications. From these three species, you can see that the red oak had generally had the highest carbon content when you got up to 900 and 1,000, but the yellow poplar actually at 1,000 was the highest, but it was different at 900. So overall, the red oak seemed to do a little bit better in terms of carbon. The willow, on the other hand, didn't do quite as well, and you can see that willow had the highest ash content. So you're sometimes concerned about what does this 5% or 4% ash content mean if you're trying to use these type of materials for electrical conductivity applications. Okay, so that brings us into how do these biomasses perform when we're using them for conductivity. So here's a simple setup to measure conductivity, and you can see the different types of biochar or carbonized material and how it worked. And what happens is you put a certain amount of this material in this die and you apply pressure. And then as you apply more pressure, obviously you're forcing these particles closer and closer, and you start getting better conductivity. So typically you would plot this conductivity measurement versus density. Mainly the key takeaway here is, if you're looking at these yellow poplar, willow, and red oak, biochar is made at 700 degrees Celsius in the bottom, you don't really get much conductivity. So it's not until you start getting to 800, 900, 1,000 degrees Celsius that you actually start seeing anything really good in terms of conductivity. So if you're producing biochar at 500 degrees Celsius, thinking you're going to be able to use that for conductive purposes, you won't be able to. But if your intention is to be using this for soil amendments, we're wasting energy by going up to this 700 degrees. So it goes back to, what are you trying to use this material for? And then that really changes how you're going to do the carbonization. Another property that's important are BT surface area, especially in terms of using this for soil amendments, but also using it for supercapacitors or for electronic type purposes. In here, you can see that there's differences in pore sizes, which become important later too. But you can see as you heat this to a higher level, you get more surface area. So you're taking out more of the cellulose, hemicellulose, lignin structure. Especially at these higher temperatures, you're taking out more of the lignin structure and turning that into carbon because everything else is pretty much gone. And you're starting to get higher surface areas and you're producing more porous structure. So this research was done without any kind of post-processing activation or activation within the process. So this activation will actually help you get better surface area. But we were really interested in this first part and seeing just how much surface area there was. So a few examples of using these materials. This one is using it, mixing it with polyvinyl alcohol in different levels and using it as a sensor. In this case, it was a pressure sensor. Here are some results on how that works as a pressure sensor by adding different percentages, anywhere from 6% up to 20% weight. If you're looking at a long range of pressure, so 0 to 350 kilopascals of applying pressure to this sensor. Adding 6% by weight is the best. It's more linear and it covers the entire range. And if you look at any of these graphs on the right, you can see once you get to a certain pressure, they just flatten out. So that means that sensor wouldn't be able to tell the difference between 200 kPa or kilopascals and 300 kilopascals of pressure on that sensor. So if you're using these sensors in, say, a robot hand to be doing some kind of automated repairs to a satellite, for instance, which is some work that we've looked at in the past, that you might be putting too much pressure on a part and actually crushing it. So it's important to get the right type of carbon in there and the right weight percentage. And then the one on the left is just showing that you get to a certain point, in this case 16%, where you don't gain any more conductivity in this type of composite. It actually gets a little bit worse. So moving a little bit away from this conductivity part, but still in the electronics field, is I mentioned this ordered structure that you can get from carbonizing in a certain way. So this research was looking at forming highly ordered mesopores carbon. You can see I have yesterday I took a screenshot of how much this carbon material goes for. So if you want to buy a 70-gram bag of activated carbon, it is $217 US. So a fairly good price per gram you get from this compared to that cowboy charcoal that you would use for heating. Wouldn't be anywhere near as expensive as this activated carbon. One of the keys to look at as we're going to the next couple slides is this particular material that's for sale is its capacitance. So it's 28 farads per gram. So you'll start seeing how that compares to some of the work we're doing. The idea is that as you're taking out and removing the hemicellulose first through carbonization, you do that first, and then you want to do the removal of the cellulose in a certain manner that you don't degrade the original biomass cellular structure. So you want to keep these really nice ordered channels, and you don't want to just blow it completely apart, which I'll show you two examples of how that, one where you, with the same species where it's just kind of messy, and the other one where you get nice ordered material. So this is the same biocarbon which I showed before. So before, the red oak performed the best in conductivity. But in this case, in terms of capacitance, the willow, which had the highest ash content, had the lowest carbon content, actually did the best in terms of capacitance. So here we're at 44 farads per gram, and I mentioned those ones for sale were around 28, if I remember right. In this case, this research was done by including these carbon materials into as electrodes in coin cell batteries, and these capacitance tests are done. So no activation done here. Following on this research was another project that was looking at doing a more stepwise kind of carbonization using the same willow material as one of the species, and then looking to see if you can improve the capacitance. So in this case, this was the results I'm showing in table 2, and in the graphs next to it are this willow that went through a pyrolysis route of different steps. So in this case, 450 to 550, it was carbonized to, and then it was stopped, and then it was later activated with CO2 up to 800 degrees Celsius and held there for 60 minutes. So this can help tell you what this activation will actually do in terms of improving your capacitance properties. So if we look in table 2, you're seeing these surface areas go up quite a bit compared to what I was showing before. So the one below where it says willow char was from the previous result. So you can see at 800 degrees C in that original research, we were at 31 or 32 square meters per gram. Under this activation type route, if you pick one of the 800s, so the BAC 830-D, surface area is at 618. So quite a huge increase in surface area. And that translates And that ordered structure also translates over to higher capacitance. So you're getting, capacitance up around, the 100 range compared to the 40 that we were getting before. So here's just some images of the differences. So the one on the right side is when you're doing this stepwise carbonization to keep that ordered structure. So you can see the channels, the original cell wall of this willow is still pretty well intact, and you can see the pores that are developed in there. On the right side is the one we're doing without really any, just going straight up to 800 degrees, let's say. And you can see this is also the same willow, and you can see this not really good ordered structure. Things are kind of broken apart and torn apart, so you don't take advantage of the nice order that you had. Okay, so that's a little bit on these electronic type applications. So I have a couple slides that I'll go through here on just using this for composites. So I have some examples of mixing this with polymers to make films, to make insulating materials, to make wood plastic composites. So here was research that we did in looking at adding different levels of biochar to polypropylene. In this case, we were able to improve the thermal properties, the water absorption properties, and mechanical properties. So in table 2 and 3, you can see generally as you add up to 25% biochar, your bending strength properties increased. Same thing with the elasticity. You actually ended up getting higher MOE values by adding this biochar in. Then we're showing the water absorption up here. So experiment 1 is 0% biochar, experiment 5 is 40%. And you can see we're just soaking these samples, and you can see that when you add this biochar, these wood plastic composites aren't uptaking as much moisture as they were when you didn't have it in there. And then in the bottom, we're just looking at weight loss. So if you're trying to improve the thermal properties of this material, adding these different levels of biochar can actually increase its thermal performance. So in a structural sense, you wouldn't maybe get as much deformation or creep under higher temperatures if this material is outside being heated by the sun, let's say. Then another kind of composite that we're looking at is using this for improving water quality. So here was a research project we had using torrefied and carbonized biomass and mixing it in with wood chips to absorb rainwater that was running off or running onto a livestock feeding, really loafing area. They weren't really feeding on it, they feed off to the side of it. But in this case, these livestock are out there doing what livestock do and making kind of a mess, and then it rains, and then that water and manure gets, typically just runs into a river. So we're looking at using this biochar is a way to improve water quality in this engineered type system. So it's about, let's see, it's a little less than maybe 3/4 of a meter deep type column that we were looking at, or bed that we were looking at. So really to study this first, we were doing some in-lab studies with tubes. We're packing the tubes with all the different kind of composite mixture that we wanted. And you can see as you go to column 5 and column 7, we have the biochar or BC included in there, and it's mixed in with other wood chips, torrefied wood chips, and also just regular wood chips. And then you can see what this cow wastewater looks like when it comes out of these different tubes. The main thing is we wanted to see what this biochar did. So the mixtures in this case that included biochar were able to actually reduce the pollutants in the water, which we're showing in these graphs, specifically total nitrogen, ammonia, and phosphorus that was running off when we were off of this potential pasture field. So last couple slides, this last one is kind of where we are now. So you're attending this FAÇADE webinar, and this is really what the FAÇADE project looks like. Using these carbonized hemp materials is an improvement or an additive for coatings in facades to improve the UV protection. So Leticia will be explaining this in much more detail later, but really what we're trying to do now is, look at other carbonization routes, such as hemp, olive stones, arundinox, and other underutilized wood species to make these carbons. I like this image on the left of the hemp that Leticia was working on. You can really see compared to, this didn't have any activation. This was a one-step. It wasn't multi-step, and you can still see this ordered structure taking place, unlike the willow that was kind of destroyed. And you can see the porous nature in this image of all the pores that are created in here. So if you take and activate this even further, I think you have even some more opportunities there. Then finally, what could possibly go wrong as you're carbonizing? Well, quite a lot. Here's one example of me catching a furnace on fire, through broken tubes, a little bit of a problem with water entering the tube. So this isn't the easiest thing to do, and there are potential things that happen as you're doing this, but in general, we've been pretty successful in making these materials. So with that, I think I probably left a few minutes for questions, hopefully, and I will end there.
Thank you, Dr. DeVallance, for this very nice presentation, and also for highlighting how dangerous is our research. Please, audience, if you have questions, type them in the chat. And I have a question for you, Dave. Do you know any industrial that already use or would be interested to use the biocarbon for conductivity applications, or more specifically for the supercapacitor application?
Yeah, so there's, to my knowledge, I mean, there's people that are producing biochar, and they're producing it mainly for these soil applications, or they're producing it in very small quantities to sell for different applications. And mainly it's, these, if you're doing it on a big scale, they're producing biochar for soil amendments. There's not a lot of industrial operations doing it for these other applications yet, and really because it's the scale of the market. So, if the market for electrode material isn't very big, and it's already kind of taken over with graphene and graphite and carbon black, that it's not economical for people to start up a large facility like this. So the first thing they need is a market. Once they get the market, they can actually do this. The same thing happens with like the torrefaction, so a lower level kind of sort of carbonization that is being used for energy markets. The market just really isn't there, and the economics don't sometimes pan out. So hopefully we will see in the future that this stuff starts displacing some of these other materials, but you need to really find that high volume user. And if you can find the high volume user, then I think these industries will take off more. A lot of people if you own a farm, people might put in a biochar producing kiln to make their own biochar there, but they're not able to control it, and you're just getting kind of these random properties that you use for soil amendments.
Thank you. There is a question from Erwin Emschau.
Okay.
Have you compared biochar with fossil-based counterparts, and what is the main differences and why?
Yeah, so from a life cycle standpoint, is that right? Or from a material standpoint?
It's not precise.
I was thinking more from the material standpoint.
Yeah, so so if we look at carbon black cannot get you this mesopores structure, which is important for capacitance. I don't have it here, but we've compared the conductivity of carbon black, of graphite, and of these different biocarbon materials. If we go back to that, if you look back at the conductivity values for, let's say, biochar, where you're at, I don't know, maybe, let me see if I can go up here. Anyways, so graphite is much more conductive than the material we're making now. So from an electrical conductivity standpoint, it might not be as good, but as you saw that carbon black used as a supercapacitor, that really can't get these mesopore structures, its capacitance was much lower than what we were seeing with some of these willow. So it really depends on the final application. It's really hard to compete with things like graphite and graphene, especially graphene, but it can be more costly in some sense to make some of those too. So I hope that answered some of your question.
Yeah, and I think you also answered the question of Henning, who was, how does the quality of carbon black from biomass compare to fossil origins? So I think we replied to this question. We have a question from VS. Can you use this biochar for making tires of cars?
Yeah, so you can use it as a filler, like they do with carbon black. So in that case, to improve the thermal performance of those tires. The one issue with a lot of these carbon materials is it does make things more brittle in some case. So you have to be a little bit careful on how much you add in there. So these polymers, when we're mixing with PVA and also mixing it with polypropylene, the material became much more brittle. You didn't have this ductility that you see with polypropylene by itself and PVA by itself. So yes, but up to a certain point.
Okay. We have a question from Antolink David. Can you produce a solid board with biochar, and what would be the binder?
Yeah, so taking the biochar and then making it into a board, right? Yeah. You could obviously any one of these type of a bio-based polymer or a polymer would bind this together. One of the images, if we go back a little bit, when we were looking at wood plastic composites, you actually see these polymers flowing into the cells or the pores of the biochar. So you actually also get some kind of mechanical fixation in that sense. And it's also hydrophobic, so we hope it bonds with polymers better. So you could use, phenolics or epoxies. People actually used epoxies in these kind of applications. One of the other things you can do instead is you can just carbonize an entire board. And then you could use it like it is if you do it okay, or you could fill it with epoxy. And I have one example sitting here next to me of a carbonized medium density fiberboard that we did. And I had an image somewhere, I think in here. And you can, turn a wood composite into a carbon material.
Okay, thank you. We don't have any more questions. So I thank you again for the nice presentation and for replying to all the questions. And I thank all the participants who joined us today. And I hope you enjoyed the webinar, and I hope you will come back to see one of the future webinars. I wish you a good day and see you later.
Thanks to you, Letitia. Thanks everyone. Have a nice day.